Today we have problem 21 from the 2024 AMC 12A competition, where it's a recurrence problem, and we're supposing that A1 is equal to 2, and the sequence of A of n's satisfies the recurrence relation A sub n minus 1 all over n minus 1 is equal to A sub n minus 1 plus 1 all over n minus 1 plus 1 for all n greater than or equal to 2. And we want to find the greatest integer less than or equal to the sum from 1 to 100 of a sub n squared. And I want to present two ways to solve this problem. One using a sort of numerical method, and the other using an analytical method. And by numerical, I mean that maybe you see this problem and you don't really see an easy way to, I guess, try to find an explicit formula for a sub n. So you just calculate the first couple of terms and see if there's a pattern and generalize. So we're given that the first term is 2, then what's the second term? Well, using the recurrence, we have a sub 2 minus 1 over 2 minus 1 is equal to a sub 1 plus 1 over, I guess, 1 plus 1. And so plugging in a sub 1, we get that a sub 2 minus 1 is equal to 2 plus 1 over 2. So a sub 2 is equal to 5 over 2. What about a sub 3? We have a sub 3 minus 1 is equal to 3 minus 1 over 3 minus 1 is equal to a sub 2 plus 1 over 2 plus 1. So a sub 3 minus 1 is equal to 7, or just 5 over 2 plus 1 over 3 times 2. And so a sub 3 is equal to 8 over 3. Sorry. It's equal to 11 over 3 plus 1. No, that's still not right. It is 5 over 3 plus 2 over 3 plus 1, which is 10 over 3. Let's do one more. A sub 4 minus 1 over 4 minus 1 is equal to a sub 3, just 10 over 3, plus 1 over 3 plus 1. Yep. So a sub 4 is equal to 13 over 3 times 4 times 3 plus 1, or 17 over 4. And so from this, can we see any pattern? Guess one thing you can notice is, 5, 10, 17, those are both one more than a perfect square. And in particular, it's the index squared, right? So I guess sort of rewriting them as as an integer plus a fraction, this is 2 plus 1. This is 2 plus 1/2. This is 3 plus 1/3. This is 4 plus 1/4. And we see the first term is just 1 plus 1 over 1, right? So we might conjecture that a sub n is n plus 1 over n. And is this the case? Well, we can just plug it into our recurrence relationship and see if it holds. Right, so we have that, we want to show that n plus 1 over n minus 1 over n minus 1 is equal to n minus 1 plus 1 over n minus 1 plus 1 all over n minus 1 plus 1. And so getting rid of the fractions, we have n squared plus 1 minus n is equal to n minus 1 squared plus 1 plus n minus 1. So n squared minus n plus 1 is equal to n squared minus 2n plus 1 plus 1, or I guess the 1's cancel out. So plus 1 plus n. So n squared minus n plus 1 is equal to n squared minus n plus 1. And this indeed holds for all n. So we have a closed form for a sub n. Yeah, that's how you get the closed form for a sub n numerically. The other way is analytically. We can derive it by manipulating the recurrence relationship. So we have a sub n minus 1 over n minus 1 is equal to a sub n minus 1 plus 1 over n minus 1 plus 1, or just a sub n minus 1 plus 1 over n. And so getting rid of the fractions, we have that n times a sub n minus n is equal to n minus 1 a sub n minus 1 plus n minus 1. And so we'd like to, I guess, sorry, I'll move the n to the other side as well. And so we see that we have these two terms that almost look similar, right? We have this is n times a sub n, and this is n minus 1 times a sub n minus 1. So we can let b, I guess they are exactly similar, exactly the same. So we can let b sub n equal to n times a sub n, right? So then we have b sub n is equal to b sub n minus 1 plus 2n minus 1. And we can continue down all the way to b sub 1, right? We have b sub n minus 1 is equal to b sub n minus 2 plus 2 times n minus 1 minus 1. And this goes until b sub 2 is equal to b sub 1 plus 2 times 2 minus 1. And so if you back substitute everything, you'll eventually get that b sub n is equal to b sub 1 plus 2 times n plus n minus 1 all the way till 2, and then minus, we'll have n minus 1 of these. So, or n minus 1 minus 1s. And so this will equal 2 times, this is the sum from 1 to n minus 1. So n times n plus 1 over 2 minus 1 minus n plus 1, which is b sub 1 plus n squared plus n minus 2 minus n plus 1, which is b sub 1 plus n squared minus 1. And we have the initial condition that we have b sub 1 is equal to 1 times a sub 1 from this definition, and we have that a sub n is 2, right, from the given problem. So this is just equal to 2. So in the end, we have that b sub n is equal to 2 plus n squared minus 1, or n squared plus 1. And now we can substitute again our definition for b sub n in terms of a sub n to solve for a sub n explicitly. So a sub n is equal to n plus 1 over n, which matches, our numerical solution. So now we need to evaluate this sum, right? To get our answer, the sum from n is equal to 1 to 100 of a sub n squared, which is just the sum from n is equal to 1 to 100 of, that should be n plus 1 over n squared, which is n squared plus 2 plus 1 over n squared. And so we can evaluate the sum term by term. The sum of the first 100 squares is just using the formula 100 times 101 times 201 all over 6, plus the sum of 102's is 200, plus the sum of I guess 1 over the first 100 terms of 1 over n squared. And so this first term will come out to 328,350 plus 200, and then again plus this last term, or 328,550 plus this last term. And so we have to figure out what this last term is. If you've seen this before, you might recognize that it's just or you might recognize that or remember that the sum from n is equal to 1 to infinity of 1 over n squared is actually pi squared over 6, which is less than 2. So that means the sum from the sum of the first 100 terms will be also I guess 1 point something, because right, we have this is 1 over 1 squared plus 1 over 2 squared, and in particular this is 1, right? So we have 1 plus some other stuff, and so that means this is between 1 and 2, and so the greatest integer less than this is 3, or I guess like this, is 328,551, and that's the answer. But if you don't remember this fact, you can still bound it by considering the sum as 1 over, or plus 1 over 2 squared plus, I'll write out the first few terms. Right, we can group them like this, and this is equal to 1 over 1 squared plus, or this will be less than 1 over 2 squared plus 1 over 2 squared plus 1 over 4 squared plus 1 over 4 squared, which is equal to 1 plus 1/2 plus 1/4 plus, I guess eventually it'll be 1/8, and so on, and this is equal to 2. And so you can still upper bound, this infinite sum by 2, so that means this first 100 terms is also upper bounded by 2, and because 1 is contained in the term, we know that it will equal 1 plus some trash. But again, we only care about the lower bound, right? Greatest integer less than or equal to it. So we get our final answer of 328,551.